15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us on this, the Space Nuts podcast, episode 209. My name is Andrew Dunkley, and with me, as always, is Professor Fred Watson, Astronomer-at-Large. Hello, Fred.
Hello, Andrew. How are you doing?
I'm quite well, sir. How are you?
Quite well too. I guess that more or less sums it up, doesn't it? And it's all you can.
Yes.
All you can ask.
Not much more to say. Yeah,
that's right.
But we carry on regardless, and there's plenty to talk about again this week, including an update on the Starlink satellite program, a planet discovered by the University of Southern Queensland, but it's more about how they did it than the discovery itself that's interesting. And we're going to follow up a story that seems to be doing the rounds, a collision between two black holes that looks to have created an explosion of light. That sounds rather spectacular. We'll also tackle some audience questions about Exo Planets. And this one fascinates me, Fred. I hope you've done your homework. Quark Matter and Quark Stars. I thought that was the stuff of myth, but we'll find out. But that's all coming up. We'll start off, Fred, with a look at the Starlink satellite program. There's an update there.
This is, I think it's certainly the 10th launch of Starlink satellites, which takes the total up to something like 600 satellites in orbit. And of course, this is the issue that has got astronomers hot under the collar all over the world, both professional and amateur, because of the amount of light that these spacecraft reflect back from the sun. And SpaceX have come to the party on this. They have been very concerned that that's the case. And so they've looked at how to mitigate this. And I think I'm right in saying that the whole tranche of, and I believe it was 57 spacecraft that were launched with probably some other payloads in as well. These are 57 of the Starlink satellites. But this whole tranche of them now uses what SpaceX is calling, they call the satellites the visor sats, because they've got a sun visor, to stop the direct light of the sun illuminating the antennas of the spacecraft, and hence, causing bright reflections or causing light pollution for astronomers trying to see the stars. These apparently are made of a foam material, a dark foam-like material that has no effect on the radio signals that are being transmitted, but will basically, prevent or certainly reduce the amount of light that comes from each spacecraft as it reflects sunlight. So their effect is yet to be seen. We might expect to see some observations of this tranche of 57 spacecraft going across the sky with their visors, and it'll be great if nobody sees anything. Well,
that's the thing, isn't it?
Yeah.
Because in the past, people have photographed these lines of lights in the sky, and we've had a few amateur astronomers message us to say that they've had issue with satellites while trying to do astrophotography.
Yep.
And if indeed they have managed to come up with a solution for that, and we did talk about that, I think last time, a few weeks ago, that they were considering this, it will be just a fantastic effort, and that's got to be a positive thing.
Very much so, yeah. So we'll wait to see what the verdict is on that. It's a good story, and
well, I suppose we'll know in the next little while. It won't take long.
Shouldn't do. Probably before this episode of Space Nuts hits the airwaves. Anyway,
yeah. How long does it take for them to deploy 57 satellites?
It's a pretty rapid process, and what has almost alarmed people in the past when they weren't aware of what was going on here is this stream of up to 60 spacecraft in a line across the sky. Very, very interesting stuff.
Yes, that's what I've seen photos of, and it does sort of catch you off guard. And I've seen a few posts where people have said, "What is it? What is it? Can someone tell me?" And then there are others in the know that say, "Oh, that's SpaceX, blah blah," and and there it is. So this time, perhaps no one will see anything.
Wouldn't it be great if nobody saw anything? Yeah.
Yeah, fingers crossed. All right, that's good news. Let's move on to this planetary discovery by the University of Southern Queensland. I know the stories about maybe how they did it, but do we know much about the planet at this stage?
Yeah, we do. It's a really interesting story, Andrew, because it's got a very strong Australian flavour. There is a strong exoplanet group at the University of Southern Queensland. Most of them I know pretty well because I've worked with many of them before on at the observatory at Siding Spring in New South Wales. The University of Southern Queensland has its own observatory. It's a place called Mount Kent. It's a dark sky site, which means that they'll be delighted that the SpaceX satellites have been darkened, because they would have certainly had interference from that. It's essentially a planet discovery facility, which is used in tandem with NASA's TESS satellite, the Transiting Exoplanet Survey satellite. Basically, University of Southern Queensland provides backup facilities, and that's exactly what's happened in this particular story. Sorry, you asked me about the star itself, the planet itself, which I'm now getting to. It is called AU Microscopiae, which means it's in the constellation of Microscopio. Gosh, I can't even say it. Microscopium. AU Microscopiae, to give it its Latin pronunciation, or usually known as AU Mic. It's
and that how Australian is that, Fred? Mic.
And well, it's
that is.
Yeah, Mick, that's right. She'll be right.
Australians have a reputation for abbreviating things, and Michael becomes Mick. So this is now Planet Mick.
It is Planet Mick, that's right. Actually, you're quite right, because it's AU Mick. AU is a designator that tells you it's a variable star, but it also means Australia. So AU.
Yes, it does.
Yeah, it's got everything going for it. So there it is. Why is this This is a young variable star. Why is it of interest? Because it has a dust debris disk around it. So it's, this is what we call a protoplanetary disk. Our sun had one once upon a time. The solar system grew within that as these particles of dust and the debris stuck together by this process called accretion. So it's got, it has been known to have this disk of debris, but now what has happened is as a planet has been found within that disk. So it's young, as I said, only 20 to 30 million years old compared with the 4.6 billion years of our solar system. And the planet has been discovered by the TESS spacecraft, the Transiting Exoplanet Survey satellite, which noted a dip in the star's brightness as the planet passed in front of it. So that's a fairly standard process. That's how TESS works, and it's how many of the exoplanets that are being discovered at the moment are being found. But what then was able to happen was that because the University of Southern Queensland has this link with the TESS facility, the information was basically passed over to the astronomers at Toowoomba, USQ, who used their telescopes, which is actually it's part of a support network called Minerva Australis. I can't remember what Minerva is an acronym for, but it's a fairly large consortium. And as I said, with telescopes at Mount Kent near Toowoomba. So the USQ astronomers used their telescopes not only to check these measurements of the change in brightness of the star, but also to carry out what's called the Doppler wobble method, which you and I have talked about before.
Yes,
as well, Andrew. So you use the light from the star, you can split it into its component spectrum colors. That reveals this barcode of information, which is imprinted by the elements in the atmosphere of the star. But by making very accurate measurements of these, you can work out the motion of the star itself as it's pulled around by the planet. And so, our sun has that effect. The sun moves backwards and forwards slightly as the different planets in the solar system move around it. Principally, it's Jupiter that does that, but the other planets have an effect too. So that has now been observed with the Mount Kent telescopes. And basically, it means that you actually extract much more information, because you can determine the mass of the transiting planet. You can also determine, by looking how far it dips the light of its parent star, you can also determine its size, and that gives you its density, which tells you something about its nature. This one is a Neptune star, a Neptune-sized planet, unlikely to be a home for life, but nevertheless part of the giant picture of exoplanets that we're building up now. It's well over 4,000 that have been discovered. So we live in a golden age of exoplanet discovery, and this is just another way in which these things can be, they can be characterized.
Yes, indeed. So they ended up confirming it with both methods, transit and Doppler wobble.
Yeah, that's right. Exactly.
Yeah. I know all about the Doppler wobble effect. I missed a short putt on Saturday because of that. It's nasty stuff.
Oh, yes, you've got to watch out for it on the golf course.
Oh, yeah. There's a lot of Doppler wobbling going on. It's terrible. That's my excuse for everything. Well, that's a great discovery, and they're doing some good work up there by the sound of it, Fred.
They are indeed. It's a paper that's gone in the journal Nature, which is the leading science journal published in the UK. The team from it's a very long list of authors in this paper, which also includes people from the University of New South Wales. I noticed Chris Tinney's name's there. Chris is an old colleague of mine, used to be at the AAO. Jonty Horner is one of the lead people up at Mount Kent Observatory in USQ. So a lot of friends and colleagues there in this large number of authors for this paper.
Jonty wouldn't be South African, would he?
He comes from not very far from where I grew up. He's got an accent that's not that different from mine, believe me.
Oh, okay. Interesting.
Well, Jonty's, I should say, it's very much a northeast of England diminutive, except when you get to Newcastle, it's Jonty, because there's a...
Of course it is.
Stop there. Why, Jonty, man. Hey, who you ganning on, Jonty? Yeah. Well,
and Mount Kent in one of the most horrible parts of Australia, the Darling Downs. What a hideous looking district.
Yeah, I think you better explain that, because you might upset people.
It's absolutely beautiful. Rolling hills and green valleys, and it's just glorious. Just a beautiful part of the world. Only just over the border. Why didn't we snaffle that when we drew up the maps, Fred? Oh. I have no idea.
Probably
anyway.
We did, actually, yeah.
Well, yeah, New South Wales, the state we live in, used to encompass all of Australia right to the West Australian border. And someone decided to carve it up, and they gave Queensland the best bit. I'm pretty unimpressed, to be honest.
Well,
but anyway, that's the way it goes.
Yeah.
That's the way it goes. You're listening to the Space Nuts podcast with Andrew Dunkley and Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, if you'd like to become a premium member of the Space Nuts Supercast franchise, well, that sounded serious, you can do that by visiting our website, spacenuts.supercast.tech, and read all about it there. There are monthly plans. This is if you want to put something back into the podcast, which is completely optional. But as a Supercast member, you get access to the back catalogue with new episodes every week, weekly new episodes, exclusive bonus AMA content, and it's 100% commercial free. So if you'd like to look that up, you can go to our website and check it out. The URL is spacenuts.supercast.tech, But you can also find out how all this works through our standard website, spacenutspodcast.com. And thank you to our patrons. We're going to be adding some bonus material in the next week or so. Now, Fred, let's move on to this story that's certainly been hitting the headlines in many, many publications, and that is the collision that's been reported between two black holes, which may have caused an explosion of light. Now, I'm guessing that's a little bit more significant than a fireworks display.
Yes, that's right. I mean, this is a little bit like the story we've just talked about. Excuse me, the planet discovery. This is a highly collaborative event between many different institutions, some of which are very, very different in their style of observing, that has made a discovery that is, well, it's a world first. It's the first time this sort of thing has been observed, a pair of black holes merging, but producing a light signal. So, okay, let's get back to basics. Black holes merging, you basically need a gravitational wave detector. And we now have working gravitational wave observatories. The LIGO facility in the United States, operated by the National Science Foundation, the Laser Interferometer Gravitational Wave Observatory, and a European version, which is called Virgo. These instruments have been operating together for a number of years now and actually producing gravitational wave detections, most of which are from either merging black holes or merging neutron stars or merging black holes with a neutron star. And you can characterize them quite accurately by looking at the wave pattern of the gravitational waves as they pass through the Earth. Because what we're talking about here is that slight shaking of space that comes about when a large mass is accelerated way, way off in the depths of space, but it shakes space around it. That causes waves. It's a bit like dropping a pebble in a pond, only a bit like it, but it's a bit like that. And, you can detect the ripples as they go past. And looking at the details of those ripples is what tells you what you're actually seeing. It is an astounding scientific discipline that has emerged since we've actually been able to detect these gravitational waves. So two black holes merging don't cause any light normally because they're black. What they do is they spiral around each other and then merge into a larger black hole, which itself, like the two precursors, is also black, and so you don't get a light flash until now. And there's an event.
Yes.
An event which I love the name. It's GW 190521G. That tells you it's an event, a gravitational wave event that occurred on the 21st of May 2019. So it's taken until now to analyze the results and get them out. But it turns out that on that day and at the time of the event, excuse me, another completely different style of telescope, which is at the Palomar Observatory near San Diego. And if I remember rightly, this is based on their Schmidt telescope, which is effectively a twin of the Schmidt telescope we have at Siding Spring Observatory here in Australia. What used to be called the 40-meter Schmidt. Two of them. Yep. One in Palomar, one here in Australia, now called the 1.2-meter Schmidt. So Caltech operate this instrument, and I'm pretty sure I'm talking about the right telescope. If I'm not, somebody must excuse me. The Zwicky Transient Facility is essentially a wide field imager that looks for transient events, things that take place over a short length of time. It's named after Fritz Zwicky, who is actually the person who discovered dark matter, among other things. He was a 20th century astronomer, sadly now no longer with us, but a character and a half, according to all accounts. The ZTF, it's called, the Zwicky Transient Facility, actually observed a flash of light at the same point that this gravitational wave disturbance seemed to come from. And so that gives you essentially a puzzle. You can look at the the shape of the gravitational wave measurements. You can determine that what you've seen is not two neutron stars colliding, but two black holes colliding. But then you've got the enigma of the fact that they produced a flash. And so the authors of the paper that has resulted from this suggest that the two black holes themselves, which are probably quite large, of order of 10 times the mass of the sun, that sort of size, but they suggest that these two black holes were in orbit around each other, but together were in orbit around a supermassive black hole. In other words, something at the center of the galaxy that's millions of times the mass of the sun, and has its accretion disk around. It's got this disk of gas and stars and bits of debris that it's kind of sucking in. And so the suspicion is that these two black holes were just part of the swirling mass of stuff going around the big black hole. When they merged, they essentially provided an acceleration. The merging accelerates the final black hole, which may have essentially somehow plowed, as the words that they use, plowed through the disk of gas, causing it to light up. It sounds like a complex story, but it seems to be the best that you can do in terms of trying to understand why two merging black holes would give you a light signal. And it's all about the environment that they're in. If they're in a dense environment with a swirling material going around a bigger supermassive black hole, then you can create this flash of light. And so what the authors are suggesting is that, given what we now can detect with gravitational wave telescopes or detectors, basically we've got a new way of essentially studying the black hole population generally. If you look for merging black holes in orbit around bigger ones, which is what this event seems to have been. So they are very excited about this. And there is one footnote in the paper, and that is kind of a bit of a disclaimer, really, because although the conclusion of this paper is that light flare that was picked up at the Zwicky Transient facility, although that is very likely to be the result of this black hole merger, there are other possibilities. And, you can imagine that it could have been just a chance occurrence of two things in the same direction, which have a completely independent source. One of them gives a flash, the other gives a gravitational wave signal, but they've nothing to do with each other. I think.
Yeah, I suppose it'd be very unlikely, but it's always a possibility, isn't it?
I think it's unlikely too. But yes, they say they cannot completely rule out other possibilities.
Yeah, fair enough. But as we've discussed before with the gravitational wave detection capabilities we now have, it's early days in terms of what we're finding and how we're detecting these things and the combinations of factors that create gravitational waves. So, as you said, we've got signatures that indicate two black holes merging, two neutron stars merging, or a neutron star merging with a black hole, but this could well be two black holes merging in a dust cloud. So, what else could possibly happen?
Exactly. So, it's either way, whatever the cause is. This is it's a big step forward. I think as well, just to perhaps give it a little bit more credibility, I think. Theoretical astronomers have already realized that maybe such events could happen, that you can get a black hole merger that gives a light flash before this one was detected. In other words, these theoretical astronomers, they think way outside the box. They imagine all kinds of scenarios. And maybe they were thinking about this beforehand, And and what this is the first confirmation of that. I'm not quite sure that that was the order in which things happened, but that's very typical of the way astronomy works.
Okay. Well, there might be more to learn on this. I'm sure they'll be doing a lot of analysis on that data and keeping their eyes open for more gravitational waves, and who knows what we'll learn from those, which I think is what I said last time, but that's the way it is. That's just the way it is at the moment.
Yeah.
It's a sort of one of the fresher areas in science and astronomy. So it's definitely a watch this space scenario, because there seems to be an accelerating amount of data coming out of gravitational wave detection technology. You're listening to the Space Nuts podcast with me, Andrew Dunkley, and of course, Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, if you would like to send us a question and see if you can stump Fred, we'll call it, that's what we'll call the segment from now on, I think. Can you stump Fred? You can send your questions to us the regular way by messenger or email or something like that via our website, or you can go to our website and click on the AMA link at the top of the page and record your question in an audio form. We love to hear your voices. We've had some great questions from people, and you know, it's nice to actually hear from you, literally. So you can do that at spacenutspodcast.com, spacenutspodcast.com. While you're there, you can check out Astronomy Daily, the Space Nuts shop, the bookshop. But the AMA link up the top will give you access to the audio recorder. You just got to have a microphone on your device, but it'll work on a smartphone, it'll work on a tablet. And if you've got a laptop, they usually have microphones built in. But if you've got a desktop with a microphone attached, then it'll work on that too. So it's pretty simple, and we'd love to hear from you. Quite literally, love to hear from you. Now, Fred, let's get to a couple of questions. No audio questions this week, but we have one from from Alex Patunley. I hope I have pronounced that correctly. Alex, thanks for your question. Hi, Andrew and Fred. I have a question about exoplanets. If we cannot see exoplanets directly and we measure their mass and yearly orbits via the wobble technique and the dipping light technique, whereby the star's light dims slightly when something allegedly passes in front of it, how can we possibly know if it's one planet's mass we are measuring? Surely a star's wobble could only be linked to a concentration of mass on one side of the star. Does that even tell us how many exoplanets that star has? And if one was viewing our own solar system from Alpha Centauri using the transit technique, then doesn't one need to train their telescope constantly at our star for the best part of 100 years plus in order to record the dips in brightness of most of our planets passing in front of the sun? Logically, one must stare at our sun for a year from Alpha Centauri in order to catch the Earth passing in front of our sun, and therefore measure our planet's mass and distance perhaps from the sun. Is that what planet hunting telescopes do? Stare at the same system or patch of sky for over a year? If they don't, then how can we ever hope to discover Earth-like planets that are close, that are not close to their suns? Red dwarfs are not the best candidates for Earth-like planets. Is it possible to discover planets in bigger orbits if we haven't had time to watch them for years and years to catch the second dip in brightness? Anyway, would be great to hear your thoughts. Keep up the good work, Alex. It's a long question, and I think we've already touched on it in this episode in terms of the wobble technique and the transit technique. But he brings up some good points. How long is long enough to make the discoveries you hope to make?
Exactly. So what Alex says is absolutely right. It's not a quick process. And okay, let's imagine the scenario that he mentions, that if you're looking at our solar system from, well, let's say the distance of Alpha Centauri, let's say you're looking in the direction that all the planets would pass in front of the sun, then what happens is you basically have to look for a long time. You watch how the star's brightness changes And in many of the planetary systems that have been discovered, yes, this is what we've seen. We've seen multiple dips, and some of them are different depths. By that I mean you're talking about a bigger planet blocking the light of its parent star. So the light dips, and then a year later it dips again, but it's a deeper dip this time. And then what you wind up doing is recording all these different dips, perhaps from several different planets. If it was our solar system, Jupiter, Saturn, the ice giants, all of them would give a different depth, and they would be on a different cadence. That's to say that they'd have a different spacing in time. You would need to watch our solar system for a very, very long time to make those discoveries. 100 years plus, that's right, because Jupiter's kind of going around in 12 years. In order to validate is the word I'm looking for. In order to validate a planet discovery, I think you have to see it dip. It's like dip 3 times. I think that's the standard. So that's 36 years for Jupiter, and this is why most of the planets that have been discovered so far are orbiting around red dwarf stars, which are much less massive than our sun, and so that the planets are closer in. They're nearer to their parent star, so they have shorter years, and that makes them much easier to pick up. It's why we often see things with a year of just a few days, because you can pick up this dip after not very much length of time in observing them. And yes, that is one of the limitations. So the TESS spacecraft, which we talked about a few minutes ago, I think if I remember right, Alex is right, they stare at a patch of sky looking for the dips in brightness. And I think with TESS, it looks at each patch of sky for, if I remember rightly, it's 27 days, which is not a very long time when you're talking about things in orbit around stars. But what you can then do is, if you find a star that clearly has a planet passing in front of it, so you've observed one dip, then you can go to other observatories, and there are now dedicated telescopes which will focus on just one star and look for the change in brightness over a long period. And in fact, that's all been turned out to citizen science as well. So amateurs now can do this with their own telescopes. Technology has come on by leaps and bounds. Just throwing in a little bit at the end, Alex talked at the beginning of his question about the Doppler wobble effect, the fact that as a planet goes around a star, it pulls the star slightly one way and the other. Once again, if you've got multiple planets, that pulling and pushing gets more complicated. And so what you get is what we call a radial velocity curve. That's a shape of the line of sight velocity of the star over time. And with a single planet, it will be just a regular up and down curve. But if you've got more than one planet, that gets really complicated. It's got little steps in it and jumps and bumps and things of that sort. But once again, you can actually analyze those and tease out exactly what it is you're looking at and discover multiple planets. So it's a long process, it's a complicated process, but it does work.
Yes, we know it does, because we've, as you said, found over 4,000 such exoplanets. But it also indicates to me, based on this hit and miss approach, I suppose, that 4,000 planets is probably a drop in the ocean in terms of what we've already, areas of space we've already observed. There's probably, for every planet we have found, if we use our own solar system as an example, probably 6 or 7 more that we haven't seen.
Absolutely, that's right. The smaller ones, our present techniques for determining or discovering planets, they're not sensitive to small planets, particularly small planets 150 million years from their parent star, like the Earth is. The Earth will be very hard to detect by the techniques that we're using at the moment. But over time, those technologies and the techniques are improving. So, yes, Earth-like planets are certainly on the agenda. But as once again, it tends to be red dwarf stars that they are orbiting around. And of course, the other thing is red dwarf stars are by far the most common stars in the whole galaxy. So that's another reason why the discovery has been, has been basically skewed towards those kinds of stars.
He mentioned Alpha Centauri as an observation point of our solar system, and the process and the time it would take to find the planets orbiting our sun. I recall, I think, that we have discovered a planet or maybe more than one planet in the Alpha Centauri region, have we?
Yes, that's right. Yeah. And in fact, I think Proxima is supposed to have an Earth-like planet around it. It's not very... Proxima is the nearest of those stars, the Alpha Centauri stars. It's not... I don't think it's a very firm observation, if I remember rightly, but there is a suspicion that there is an Earth-sized planet in orbit around Proxima Centauri.
Interesting.
Just one more loose end, if I may. Sorry. If you were on Alpha Centauri, you wouldn't see the planets of the solar system crossing in front of the sun because you're in the wrong direction, which is why I think I said, seen from a star at the distance of Alpha Centauri, the Alpha Centauri is well away from the plane of the solar system.
Oh, okay. Yes, of course.
See what I mean? So you're not going to see... Yeah. You're never going to see the solar system's planets crossing the sun from that direction. But there are other directions that you would see it from.
Yes, indeed. All right. Alex, thank you for your question. Well asked, and hopefully we gave you an adequate answer here on Space Nuts. Now, Fred, let's move on to our next question. This one comes from John Pitts. Hello from Walloon, Queensland. Andrew and Fred, I have a double bunger for you, or maybe it's the same question twice. There was a recent announcement of evidence that neutron stars may contain something called quark matter in their cores. I hadn't heard of this before. Can you please tell me what quark matter might be? I know it's inside golf balls. I'm guessing it's an even more dense matter or state of matter than that in the neutron star. Also, in the past week, it's been announced that gravitational waves from a collision between 23 solar mass black holes and an object of 2.6 solar masses. This object is heavier than neutron stars are supposed to be and lighter than any black hole previously observed. It could be a small black hole or a neutron star or something else. One of the possible something else candidates is a Quark Star, which I suppose is made entirely of the aforementioned quark matter. How could a Quark Star differ from a neutron star? Brought up something very juicy and interesting, and something we certainly have never talked about before, John, and that is quark matter and quark stars. So over to you, Fred.
Okay. So quarks are... they are among the fundamental building blocks of matter. And so the standard model of matter involves actually 16 particles, 17 if you include the Higgs boson, which is the particle that gives all the others mass. So there are 4 force particles. There are 6 leptons, which include things like electrons and muons. These are, basically small subatomic particles. And then there are 6 quarks. And that together makes up the 16 plus 1 particles of subatomic matter. What I love about quarks is the names that they've got. These 6 quarks have got different names. They are up, down, top, bottom, charm, and strange.
Oh, good grief.
Yeah. And they're all different. So they are specifically, individually determined components of the building blocks of matter. They're what you and I are made of. You've got a strange quark in your digestive system. It's probably well in other places as well. So anyway, quarks they're the components of things like protons and neutrons, and that's really the nub of the matter when it comes to stars. So we recognize several states of what's called degenerate matter in astronomy, and they're characterized by...
They're teenage quarks. are they?
I'm sorry, I missed the word there. They're what?
The teenage quarks, teen quarks, degenerate matter.
I wasn't degenerate when I was a teenager. I was a nice lad.
Pretty sure I was.
Yeah. Okay, what's degenerate matter? It's matter that's in a very unusual state. And the example that most of us think of are white dwarf stars, which are, in fact, that's the end product of the sun. The sun will wind up as a white dwarf star, something with almost the mass of the sun, but which is about the size of the Earth. And it's compressed to such a density that it's only the outward pressure of the electrons that is stopping it from collapsing to another stage of density. So this is called electron degeneracy, when the electrons are what's holding stuff apart. The next stage, if it's more massive than 1.4 times the mass of the sun, then it will continue collapsing until it gets to what we call neutron degeneracy, where just the pressure of the neutrons is stopping it collapsing further. And that's a neutron star. So these are, of the order of 10 to 20 kilometers across, but once again, with the mass of a star in them. And exactly as John was saying, sorry, John, I mixed you up with Alex for a minute there. Exactly as John was saying, that's the kind of typical picture of what we imagine to be the most dense kind of star. And until now, they have been thought not to exist more than about twice the mass of the sun. And the thinking has been that if you get a neutron star with more than 2 solar masses of matter in it, it will continue its gravitational collapse. It's the force of gravity that does this, of course, pulls it down to be a black hole, and nothing can can stop it from collapsing into that. So what's put a spanner in the works, exactly as John says, is observations made recently which seem to suggest that there are neutron stars which are more massive than that 2 solar mass limit, and in particular one of a solar mass of 2.6, a mass of 2.6 solar masses. So what is it? It's somewhere between a black hole and a neutron star, or is it something else? And that's where the idea of quark stars comes in to the picture. Because there is work, this has been done, and thanks, John, for pointing this out, in the University of Helsinki and elsewhere. It's work done by a theoretical group there. What they are suggesting is that neutron stars might be more complicated than we thought. And they might have a structure. Now, we know that already from previous work, which suggests that neutron stars in their outer layers have probably got a high proportion of protons as well. You've got to have protons there somehow, because these things are highly magnetic and neutrons are magnetized. So there is the thinking that a neutron star might be a bit like an orange with an outer layer that's rich in protons, and then a neutron core. But the new work suggests that maybe there is more to it than we thought, and they might have a quark core at the center of a neutron star. So you've got this change in density from the outside to the edge, and in the middle you've got this really exotic stuff, which is kind of predicted by theory, that quark matter, things that are only stopped from turning into a black hole by the quarks themselves, the ups, the downs, the bottoms and tops and charms and strange, although it might not be all of them. I'm not enough of a particle physicist to know which are prohibited and which are allowed. So
my brain's falling apart. This is,
it's new, wow. Great stuff. People have talked about quark stars for a long time, but this seems to be the first time that it's really come into the regime of something that is worth following up, rather than something that is highly speculative. It's still pretty speculative, but it looks as though it's heading for the mainstream. And certainly this group in Finland think that quark stars, or this exotic state of quark matter, might well be a very likely outcome. There's a quotation here by one of the lead scientists of this work, which is, there is still a small but non-zero chance that all neutron stars are composed of nuclear matter alone. What we've been able to do, however, is quantify what this scenario would require. In short, the behavior of dense nuclear matter would then need to be truly peculiar. For instance, the speed of sound would need to reach almost that of light. So this is what they're saying here, is this is a scenario where you don't have the quarks in it, where you've just got neutrons. And what it says is you get very peculiar outcomes. So I think everybody's leaning towards the idea that maybe we are starting to discover quark stars.
So it's possible that
watch this
in the
space.
future we could reclassify some stars as quark rather than whatever they are at the moment.
Rather than neutrons. Yeah, rather than massive neutron stars. That's right.
Yeah. Fascinating. Interesting. Yeah. Nice to open a new door on Space Nuts too, and appreciate the question. Thank you. It was John, wasn't it?
Thank you.
Yeah.
And if it's any consolation, Andrew, it makes my brain hurt as well.
Yeah, it is. You're starting to get into the. Well, I suppose this is. You wouldn't call it science fiction, but it's science theory. But it's now starting to sort of crack into the reality side of things, and may become as you said, may become a mainstream science. And if they can make some more discoveries and more, understand more about what's going on, it's just one of the fascinating things about astronomy. It just keeps throwing up all these curveballs that you've got to try and figure out, and more and more questions to answer. But that's what it's all about. You keep going until there are no questions left to answer, which could take a long time.
Yeah, I think that'll outlast you and I.
Yeah, most possibly. But anyway, thanks, John. Appreciate the question, and hope you're well up in sunny Queensland and staying safe. That's just about it for us for another week. Fred, thank you so much.
It's a pleasure. Always good to stretch the brain. We'll see you soon.
Indeed. Feels quite stretched. Yes. All right. Catch you very soon. Fred Watson, Astronomer-at-Large. And don't forget to visit us if you're a Facebook follower on the Space Nuts Facebook page. We have quite a following there. But you might also like to join the Space Nuts podcast group on Facebook and talk to each other, because that's what the group was created for, so that Space Nuts fans could all get together and chit-chat about astronomy and share their astronomical photographs and just articles that they've come across. It's a great platform to keep in touch with each other, so you might want to consider that. Or you can do what I do and wait till the next edition of Space Nuts. I'll see you then.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.